Welcome to Study Loop.
In this question, we have a half mole of ideal gas taken from state A to state C, as shown in the figure 19.40. And we are asked to calculate the final temperature of the gas, calculate the work done on or by the gas as it moves from A to C, as well as comment on whether or not the heat leaves the system or enters the system during this process. So to go ahead and get started, let's calculate the final temperature of the gas. So the figure 19.40 is a PV diagram. So if we want to go ahead and calculate the temperature of the gas, all we need to do is read off P and V in state C and use the formula PV is equal to nRT. So in the final states, if we look at that figure, we see that V is equal to 0.004 and P is equal to 2 times 10 to the 5. This is in pascals and this is meters cubed. So to calculate the temperature, we can rearrange the standard formula here. So that's going to be PV over nR. So we just go ahead and plug everything in. And the N is the number of moles, so we use the 0.5. And R is a constant. It's about 8.31. So once we do that calculation, we get a value of about 193 kelvins. So that's the final temperature of the gas. In part B, we're asked to calculate the work done on or by the gas. So when you're given a PV diagram, it's actually pretty easy to find the work because all you need to do is calculate the area underneath the curve, and that will give you the work done. So area under PV curve, that will give you the work. So let's go ahead and calculate that. So we've got the curve generally looking something like this. So I'm going to split this into two areas here. So we'll do a rectangle like this. And then I'll do an area for the triangle piece as well. Okay, so something like that for the curve. Okay, so the area of the rectangle, we can see that the base is 0.002. And then the height of the rectangle, if we look on the graph, that is 2 times 10 to the 5. And then I'm going to add that to the area of that little triangle. The height of the triangle is 2 times 10 to the 5. The base of the triangle is 0.001. And we're going to divide that by 2 since it's a triangle. So the total area under the graph here is 500. Since the pressure is measured in pascals and the volume in meters cubed, this is 500 joules. So the only other thing that we need to figure out is, is this the work done by or the work done on the system? So on a PV diagram, if you've got the arrows pointing like this in the positive V direction, this is going to be work done by. If the arrows are pointing in the other direction, in the negative V direction, then that's going to be work done on. So this is work done by the gas. So the gas is expanding and it is doing work on its surroundings, so it's actually losing energy due to the expansion. So that's something to keep in mind as we go to part C. And part C asks us, does heat leave or enter the system during this process, as well as how much heat? So basically, to understand this, we need to understand that the change in energy, the change in internal energy of a gas is composed of both the work done by the gas as well as the heat. So any changes in the internal temperature, any changes in the internal temperature or the internal energy of the gas are composed of the work as well as heat either entering or leaving the system. So in order to be able to calculate what Q has to be in this system, we already know work, so we're going to have to figure out what the change in internal energy is. So the internal energy of an ideal gas can be calculated using this formula. So basically, the energy here is exactly proportional to the temperature. So any change in temperature really dictates the change in internal energy for the ideal gas. Now, we already calculated the final energy as 195 Kelvin, I believe, or no, 193. And if we do another calculation for the initial temperature of the gas, you'll actually see, using the exact same formula, the exact same process, you'll actually see that the initial temperature is exactly the same. So the change in temperature here is 0, and so the change in internal energy also has to be 0. So basically what we get is that the work and the heat have to balance each other out, right? Work plus heat has to equal 0. Since work is being done by the gas, the system is losing energy due to the work term. And so heat must be flowing into the system in order to replace that energy. Okay, so the total energy has to stay the same. So any energy that we lose due to work has to be replaced by the heat. So heat is going to enter the system. And it has to, numerically speaking, be exactly balanced out by the work in this situation. So that means that there's going to be exactly 500 joules of heat. Okay, so that's the final answer there to part C. Now, just a small note, this formula here, there are many different forms of it throughout physics and chemistry. So if it's not quite what you're used to seeing, like you're maybe used to seeing a negative sign there, don't worry too much about it. The point here is that any work that is lost, any work that is done by the system, that's energy lost. And so that has to be replaced with heat entering the system or energy entering the system through heat. So that's going to be it for this calculation.